if you want to discuss more about some of the more open-ended questions, yeah, we can do also during coffee break. Over beer as well, yes. Maybe for the part of the career prospects, and yes. Anyhow, okay, so what we saw yesterday was we solved the propagation of a gravitational wave in cosmology, in Friedmann-Robertson-Walker background, FRW. And to solve that, we took advantage of the fact that the wavelength of the gravitational wave from the compact binaries that we observe is much, much smaller than the relevant scales for the expansion of the universe that you can take as the horizon scale. And therefore, we didn't have to solve the full propagation equation in curved spacetime, and we were able to do the short wave expansion. So doing that, what we found out is that the strain of the H plus polarization that we observe in our detectors actually scales inversely with the luminosity distance. And then we found out that instead of having directly the shear mass, that is the quantity that we found the day before, that is the determining at leading order the shape of the gravitational wave and the chirping, instead of having the shear mass itself, we have the detector shear mass that I'm going to remind you in a second what it is. And then the rest is the same if we express everything in the frame of the observer, which is what we can observe, so it's the right thing to do. And then, yeah, so this is the rest of the part. We have also the phase. The phase also, or the chirping of the signal, if you want, also scales only with the detector frame masses. So that's something which is important. Let me just write everything for completeness. And then, yeah, these detector frame masses just carry the redshift due to the stretch of the wave. And then the other quantity, important quantity for cosmology, is the luminosity distance that carry information over the expansion rate through this integral. Yes, was this clear? So then what we did was actually see the projection of this wave into the detector. And what we found out is that the thing that we detect, the strain, is actually a combination of the two polarizations through the antenna pattern functions. So I'm not going to write again the functions, but they depend on the sky position and the polarization angle of the wave. And it's a sum over the two of them. So in general, in a single, in each detector, you have sensitivity, you detect a combination of both polarizations. If you have multiple detectors, you detect something different, so then you can extract some of the polarization information from there. The other important thing that we, just taking that into account, is that when we are thinking of these binaries, that at first order we were only caring about their masses, we should also think that they could have spins. And actually, so in general, we have to define the waveform with the masses, also the spins, but also we saw yesterday that we need to fix some reference phase at a reference time. And then we have also the luminosity distance, which is degenerate with the inclination angle. and then we have the sky position and the polarization angle. So in total, at least the standard waveforms that we use nowadays, they have 15 dimensions. And this is something that tomorrow we will touch a little bit on. This has implications for the data analysis because many of these parameters, they are actually degenerate with each other. So it's difficult to disentangle one from the other. Are there questions from yesterday at this point? Okay, so what I wish to do now is to just make a bit of a repetition, actually, of what I said during the colloquium about the three different type of sirens that we have in cosmology. But I want to do it so that you all have the opportunity to ask more questions if needed, because I think this is very important. But the main idea we already saw yesterday is the fact that we have information of cosmology through two main channels. The first one and most important is through the luminosity distance, because that's a direct observable that we have from gravitational waves. And then also indirectly through the masses, we also have information of information of the redshift. So the name also of a standard siren, you may know, is also in analogy to the other ways that we have in cosmology to measure distances. In particular, supernovae of type 1a, they are called like standard candles because you can standardize their luminosity function. And you could also use, for example, the baryon acoustic oscillation scale that was mentioned in the other lectures as a reference scale, and that's also known as standard rulers. Here, actually, the big difference is that we have an absolute, like a direct measurement of distance. But then the counter argument is that we don't have, do not have direct information of the redshift. So if you want, in gravitational waves, we are mostly on the opposite side of most of the electromagnetic observations. So the first way to get some information about cosmology is if you get some information of direct information of the redshift from the same source. That's called, we nowadays refer as bright sirens, and I know some of you are actually directly working on it. But essentially, the main idea is that you observe, you have observation of like electromagnetic counterpart, and that information of the electromagnetic counterpart allows you to get some redshift, so you can, for example, identify the host galaxy, and then from there, you get the redshift. So typically, when you are in this situation, the error that you get in the redshift is very small. So actually, most of the uncertainty. So when you have inference, for example, of H naught, if you are thinking of sources which are nearby, most of the error in H naught will come mostly from the error in the luminosity distance. And most of the error in the luminosity distance actually also comes from the degeneracy with the inclination angle. So that's something which is important. The case that we have observed for bright sirens is that of coalescence of a binary neutron star. And there was a video in the colloquium in which you could see that as they merge, essentially this signal launches a jet, which is a short gamma ray burst, which in this case arrived to the detectors like 1.5, I think, or 1 point something 7 seconds later than the gravitational waves. And then the other thing that you have is a more like a donut around the signal, which is the ejection of material that then is going to radiate actually in all the wavelengths eventually. And it's really absolutely impressive if you look at the how many telescopes detected this signal 17.17 is what really observed in all the frequencies of the electromagnetic spectrum. One thing here which is important is that so this is known as this is the kilonova. Kilonova comes because it's 1,000 times the energy of a nova. Something to take into account here is that actually the short gamma ray burst can be seen much farther away than the kilonova, but then the short gamma ray burst it's only can be viewed in a small region. So there is an opening angle which is still uncertain, but I believe people think that this opening angle is about 10 degrees. So what this means is that if you only a fraction of the binary neutron stars will be pointing at us, so for only a fraction of them we will observe the short gamma ray. So while the emission of the kilonova it's much more broad, and then could be observed. It's easier to observe if it's closer, if the signal is closer. Something to take into account as well, two things, is that if you have a neutron star and a black hole, then you could also emit electromagnetic radiation because you have the matter from the neutron star. However, you need the masses to be comparable. Because otherwise, the black hole eats very rapidly the neutron star, and then there is no time for emission. The other thing which is important, which is interesting as well, is that if a black hole merges in some environment that is dense enough, potentially it could make some sort of electromagnetic emission. And in particular, in this case, what people speculate about is that if you have a supermassive black hole, some active galactic nuclei, and then in the disk of this active galactic nuclei, you have a binary that is merging. This could potentially lead to some flare that potentially we could observe. I think this is super interesting, but in my opinion, also very difficult to identify because actually things, the signal is not so clear, and then, I don't know, AGNs, for example, their flares, they change constantly over time. So it's very difficult to know if there is something which is coming from a merger or not. But there's been claims in the literature about this. So that's something to, that is interesting. Are there questions about bright silence? Yes. Yes? Sorry, maybe can I correct you for a sec? Just maybe clarify what I meant. What I was mean, the scenario that I'm thinking here is the binary is within the disk. Sorry, yes. Okay, okay. I see your question. Yeah, so I was, yeah, thank you for that. Actually, very good point. So in my head, I was biased to thinking of current detectors. And for current detectors, because of the wavelength that we observe, you are interested in small black holes that merge. But if you think, for example, in future detectors, such as LISA, LISA will observe supermassive black holes that coalesce. Actually, in those cases, as you are rightly pointing out, there is a dense environment as well, and you could, and people, I think, are optimistic that some of them would emit. So that, I think, yeah, we should definitely add here super massive binary black holes to this list because that could also lead. Yeah, thank you for that. Yes. 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 Yeah, that's actually a great question that I'm going over the main concept, but this is very important actually. The fact that when you are close by, you are more sensitive to the fact that the binary could be moving itself within the galaxy, or the galaxy also could be moving different from the Hubble flow. So all of that you need to take into account to the estimations of the errors. Yes. As you go to far away redshifts, that you worry less. But yeah, that's a good point. Are there more questions? Yes. I think that as you go farther away, the relative effect to us is smaller, just because, yeah, you could think of in terms of triangle, or I don't know, like in terms of angles. If something is moving, which is closer by, it's gonna reach like at the same distance, it's gonna be a bigger angle that we see. But if you are farther away, that's a smaller. I don't know. Maybe that's a very hand-wavy argument, but I think it goes in that line. Yeah. Yes. So the question was how we can observe the electromagnetic counterpart of supermassive black hole binaries. Well, so that's actually, there are, so there is no evidence yet of this, but actually this is something that observers are looking for, because actually what happens is that because you have, so you would have the two supermassive black holes, and then they will have a disk around them. And what people have shown is that there could be some periodic signals periodic electromagnetic emission that carries the same period driven by the in spiral of the black holes. So actually, people are looking for these periodic patterns in the emissions as a way of proving that there is not only one black hole, but two in the center of a galaxy. I think what it will be really amazing when Lisa is online, of course, is if you could have both, and then you are seeing before merger this periodic, this emission in electromagnetic spectrum, and then in gravitational waves. I think people are thinking about different strategies. I think X-rays, people are thinking for that to detect them, but I don't know all the details about that. Yeah, yes. No, so the Hawking radiation, the time scale is much longer than the lifetime of these black hole masses. So the bigger the black hole, the slower it is. So I think that's one could neglect that effect. Okay, so the other thing that you can do, the next thing that you can do, if you don't have an electromagnetic counterpart, is actually cross-correlate, check if there are known galaxies within the localization error of your gravitational waves. So we saw yesterday that with the timing information of the arrival time of the waves in the different detectors on Earth, you can get some GW sky map. And then we also have we also have some error for the luminosity distance. And then you can ask, okay, do I have any galaxy catalog that is covering this distance range and this patch of the sky? And then what are the galaxies which are here within my localization error volume? So if you do that, what you can do is you can obtain, you can essentially say that your gravitational waves needs to come from some of the galaxies that are within this volume. So typically what happens is that, for example, if you are thinking of your inference of H naught, then what happens is that you will get something which is pretty inhomogeneous for different events. You may have weird things, but the whole point, because of course, for different parts of the sky, there might be different number of galaxies, but the main point is that eventually, if you keep stacking all of these events, eventually you would get some distribution for your, this is the total, and these are the individuals. Some distribution that traces the true cosmology. And something that was brought up in the question session yesterday is that something which is very important is the completeness, understanding the completeness of the galaxy catalog. You need to know how catalog. You need to know, if your survey is sensitive to all the possible galaxies, and if not, what type of galaxies are you are less sensitive to? Yes. Sorry, can I? Yes. So Yeah, so each survey is going to have a depth, like a apparent magnitude that can go down to. So that limits, for example, in terms of distance. And then I think depending on how many filters you have, you can also have different number of galaxies. So typically, yeah, yeah, the question is like if you are quantifying the completeness, like when you start to decrease, if this is 1, so at low redshift, presumably you detect all the galaxies within your survey area, but eventually this is going to decrease. But you need to understand this very well. Yes, yes. So here, the only thing you are, for this context, the only thing you care is you want to have redshift information, and that's what you are trying to extract from here. The subhello mass function can be relevant for other things, for example, for lensing, that I'm going to speak a bit later, but not for this matter specifically. Yes? So, sorry, can you repeat? Exactly. So, yeah, so from these two things is GW data. And then these points is the galaxy catalog. Yes. So this is something that we are going to see tomorrow, actually. But the relative error in the luminosity distance scales, roughly speaking, with the signal to noise. It's actually a bit larger than that, but so you can, and something that we will see tomorrow as well, is that typical detection thresholds are, people say, like about 8. So what this means is that at least you will have errors of 10s to 20 to 30% actually in the luminosity distance. No, well, sorry. So the signal to noise, the farther you are, so if you have a signal which is closer, then that's going to be louder, and then you're going to have a smaller error. Yes. Yes. Yes, but sorry, but are you referring to the error in the redshift or in the luminosity distance? Yeah. Okay, yes. So, yeah, in surveys, galaxy surveys, you are thinking in typically in redshift space. For gravitational waves, the difference is that we are thinking in luminosity distance space. So the farther, the larger is the luminosity distance, the larger would be the error. Yes, but that's a good analogy. Yes, sorry. Yes, so this is independent of the additional information. So that's a property of the gravitational wave themselves. So that error is that's a good question. Okay. So the other method that I want to highlight as well, it's the spectral siren method. So this is a method that what is doing is essentially make the most out of the fact that the waves they are being stretched by the cosmic expansion, and therefore, when you observe, if you observe your detector frame masses, and you count how many of them you have. Of course, in reality, we are not really counting in that sense. We are doing hierarchical Bayesian inference, and we take selection functions, but that's, I mean, I think that's a bit of a detail. The main idea is essentially that if you have something at close by, at a small luminosity distance, and then you have something at a higher luminosity distance. Let's say this is 3 gigaparsec. This is 1 gigaparsec. And then this shift here of all your mass spectrum is coming from the fact that you have this 1 plus c. So this is something which is actually the reason why it's called spectral science is because this is in some way analogous to when you look for the spectra of galaxies that you are trying to get the emissions. Well, I'm doing this terribly. I'm going to even erase it. But when you are doing the spectra of galaxies, you look for absorption lines, and you see how much they have been shifted in order to identify the redshift. Conceptually, this can be a reminiscent of that. I think the interesting thing of this method is that it only uses GW data only, and it can be applied to any, and this is important, to any compact binary. So actually here, you could have your distribution of black holes, but you could have your distribution of neutron stars, or you could have the distribution of both of them. Now, of course, the difficulty of this method is that you need to get very precise observations of the population distribution. So this requires a lot of events. A lot of events. Yes, and the other thing which is important to have to take into account is that the mass spectrum itself, it could also change with redshift. And that's because the environment in which the black holes are formed, it changes over time. Now, so let me write it here. The mass spectrum may evolve. Now, in order for this to be fully degenerate with the cosmology, actually you would need to have all your features in your mass spectrum to be changing at the same rate that cosmology is predicting. So a given cosmological model has actually a very clear prediction of how much redshifting you get at different luminosity distance. And moreover, we don't expect all the masses to evolve in the same way. So in particular, we do expect the high mass end of the spectrum to be more sensitive to the environments. So if for example, you want to form a black hole of 100 solar masses, that's something that, well, maybe 100 is too much, but if you want to do like something of 60 solar masses, that's something that is easier if you are earlier in the universe, because then your environments have, you have a lower metallicity, lower winds, and then you can form these bigger black holes. But on the other hand, at low masses, we actually don't expect so much the environment to play a role. So we do expect the mass spectrum at low masses to be more constant over redshift. So I think in that sense, I'm quite optimistic about this method, but also I've been working a lot on it, so just so that you know. Other questions? Yes. Yes, so you, so this is a plot that I'm going to show tomorrow. But if you think of the errors that you have in H of C, essentially they are going to depend, they are going to vary over redshift. So this is the relative error. And essentially, you are going to have a smaller error in the region when you have more mergers. So the more mergers, it's going to help you having a narrower, a better constraint. Yeah. More questions? Yes. 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 Yes, thank you for that question. Actually, when you are doing the dark science method, you are implicitly assuming some astrophysical distribution for your masses. So actually, implicitly, you are fixing your mass spectrum. And that actually can bias your results. So actually, indeed, what you need to do, and this is what people realized a few years ago and people are doing now, is that actually you need to do both of them simultaneously. And tomorrow I will also show you some plots in which you see that the dark side method with different assumptions about the cosmology is actually giving you, about the astrophysics, is giving you very different results. So actually, what I would argue is that you always need to do this, and then if you have good localizations, you do this, and then if you are lucky, you do this. But that's, I went this way for a pedagogical reason. I think actually in terms of data analysis should go the other way. Yeah, exactly. Yes, you said it right. It's something that we have not seen in the course, but when you are doing Bayesian inference, you need to estimate also your selection function, and that's dependent on what you are assuming for that. Yeah. Yeah, so yeah, I think this is an oversimplification that I made to explain you this. Actually, what you are doing in practice is that you take all of the events in your catalog and then you infer at the same time the mass distribution, and also you infer at the same time the merger rate, so how many events you have as a function of redshift. This is a quantity that we also infer from the data. So actually, you are doing this and this simultaneously. Yeah. And that's why I was saying, related to the previous question, that, for example, whenever your merger rate is higher, whatever this redshift is, which I told you in the first lecture, that should be between redshift 1 and 2. That's going to be the place where you're going to have the best sensitivity using this method eventually. Of course, at the moment, you are limited by the sensitivity of your detector, so maybe at the moment now, the errors already go down, go up earlier in redshift. But if you have a sensitive enough detector, the best constraint would be where you have more mergers. Okay, any more questions for the sirens? I'm going to change slightly topics, so yes. Yes? No, you're trying to infer the redshift because. Okay, yes, so the point is, so normally, when we do the astrophysical inference, forgetting about cosmology, what we do is we fix the cosmological model, and then if you fix the cosmological model from the luminosity distance, you directly get the redshift. So, and also from the detector frame masses, you directly get the source masses. Now, if you care about cosmology, what you need to do is you want to infer your cosmological parameters. We saw that the cosmological parameters which are within your Hubble rate, and then your mapping between luminosity distance and redshift is subject to the cosmological parameters. So what you are doing here is that you are, if you want, you are extracting from the data the properties of your population for different cosmologies. And then the cosmology that fits best the data and the population model that fits best the data, that's what you infer. So you're doing simultaneously the astrophysics and the cosmology. No, so for every event, you can make these relations. So every event will have some error in the luminosity distance. But for every point, if you want, every sample if you're in your posterior, you can play this game. So actually, it's self-consistent. What happens, though, is that if you have very few events, or if your mass spectrum doesn't have sharp features, then this method barely works because you need to have something that when you are doing the data analysis is clearly defined. But we do have actually features in the mass spectrum, and we will also see that tomorrow with some plots. Yes? Oh, yeah. Yes, so that's actually something that I didn't mention, but actually a lot of people do ask me in the breaks about, for example, the possibility to distinguish between a black hole and a neutron star just from the gravitational wave waveform. And actually, you can distinguish between the two because not when you are far away, both of them, they are essentially like point masses. But as they get closer to each other, then the fact that the neutron star can be deformed, that's something that imprints a small effect in the waveform close to the merger. Now, this parameter that controls how much you deform the neutron star is called the tidal deformability. And that tidal deformability is determined by the composition of the neutron star. And the neutron composition of the neutron star is determined by the equation of state of the neutron star. So if you know the equation of state of the neutron star, then you can predict the tidal deformability, and that's something actually which is not gonna change with redshift. So if you know the equation of state, then from the observations, you could also infer some cosmological information. Actually, what you would need to do in practice, I mean, so people have done like, had this idea a long time ago, which is, I think is really amazing, I mean, to do that, but actually in practice, the problem is that we don't really know the equation of state of neutron stars, but actually you could do something similar to here, in the sense that from the observations themselves, you could infer the equation of state and the cosmology, and you could get some constraints as well. Yeah, thanks for that. Okay, so I'm gonna be moving to lensing of gravitational waves, and try to give you some flavor of the different, how you solve the lensing of gravitational waves, and the main phenomenology that you have. I'm not gonna have time to go into all the details of the derivation, but rather just take you in a shortcut, and I would like actually to spend most of to make a larger emphasis on the phenomenology, because that's actually, I mean, in terms of observations and searches, that's what is most important. And in the lecture notes, there is the detailed derivations of the things that we are going to talk today. So hopefully, when we skip some of the steps, yeah, you can follow them. This is quite an exercise, cleaning all these blackboards. But it's good, it's good. Then I don't need to go to the gym after the lectures. Although I saw a lot of you were going, which is great. You were not lying when you were saying the first day that you like to do sports. Okay, I'm erasing everything because now, just so that we have a space to go over all the details of lensing at once. Okay, so we are going to study gravitational wave lensing. And the main idea, of course, is that in general relativity, waves, they fill the curvature of space and time. And then if you have your binary emitting waves, we have seen the propagation of this in a cosmological background. But if you have some inhomogeneity, that's going to affect the trajectory of the waves, and it could also potentially affect the shape of the waves. So what we want to do is to make a mapping between the source and the observer through some lens equation that we are gonna study. So the general metric that we are gonna be thinking about is again our cosmological metric. This is in conformal time, where we have the Minkowski metric, but then what we are gonna add is we are gonna add some perturbation, which is gonna be given by the lens itself. So this lens is gonna have some energy momentum tensor that we are gonna assume is static and is defined by some energy density. So then actually the the metric that one needs to study is just the case when this is a linear perturbation. This is just just a Newtonian potential here. Square. And then you see that many of these things are appearing in all the lectures, but again, yeah, this is the Poisson equation that relates the gravitational potential to the energy density. And then what we would be thinking in this case, we want to focus on situations in which this gravitational potential is really small, so that we are in this linear regime. And if you think, for example, of something which is spherically symmetric, one could argue that then this gravitational potential would be, I mean, you could think that it scales with the Schwarzschild radius over the distance. So essentially what we are saying is that we are we are in situations in which we don't have actually so compact objects, or that we are far from them. Okay, so if you are in this regime, essentially this simplifies a lot, because you remember that in general we had to account for this propagation equation, but actually it's funny that I keep writing it, but I keep also neglecting the Riemann tensor, and and actually in this case it's going to be the same. So what happens is that when we are in this, we can neglect this term when we are in this weak field gravity regime. And this is something actually that you can also show if you, for example, do like the linear, the composition of the Riemann in linear perturbations. You can see actually over a Friedmann-Robertson-Walker background, actually that the tensor modes and the scalar modes, they decouple. So that's good, because what this means actually is that then we just need to bother about an equation which is much simpler, which actually yesterday we did already solve for the case of cosmology. Now, what we want to worry is about adding this gravitational potential. Is this clear? It's very interesting, though, actually, to try to go to situations in which this is not longer the case, and then you have corrections to this. And in particular, people have been studying when you have lensing by a black hole, and the wave is very close to the black hole. Then you could actually see some of the effects of the Riemann that can mix the polarizations. But that's not something that we are going to deal with, because it's not really relevant for the context of astrophysical lenses, because typically we are going to be in situations, in cosmological setups, in which distances between source and lens are very large, and therefore it's very unlikely that you are passing so close to a lens so that this is relevant. So the derivation of the of how to solve lensing is actually quite involved. So I'm gonna actually jump over most of it, but maybe, well, let me do schematically the steps. So one starts actually just with this equation that we saw yesterday that you can compute in terms of partial derivatives if you include the square root of determinants. So we saw this yesterday. So if you take this ansatz and to make it easier, you can forget about the scale factor actually and just focus on a perturbation in a flat spacetime. If you do that, then essentially what you need to do is you need to expand this equation, and then you need to linearize in phi. So when you get this inverse and these determinants, you may have some phi's in the denominator. You can linearize that, and eventually you can get to an equation of this sort, which has been highly simplified. And then what is useful is to actually go to Fourier space. And then when you go to Fourier space, you can rewrite this equation. Here, the tilde comes from the Fourier space function. You can rewrite this equation in this way, which is a Helmholtz equation, which has also appeared in the lectures. So this is the equation you want to solve. And what is typical in the context of gravitational wave lensing or wave optics lensing is to, instead of solving in terms of your perturbation, your gravitational wave in this case, or your electromagnetic field, you can try to extract the effect of the initial conditions by defining some function f, which is the ratio of your solution divided by the initial, divided by the solution in the absence of phi. So this is the solution when phi is equals to 0. So this is will be proportional, would be an spherical wave, as we have seen. So this and this is normally called the amplification function. And it's useful in the context of lensing because in some way doing that, you are eliminating this, the effect of the source, the incoming wave, and then you have something that just tells you about generic waves propagating around the lens. Yes? No, sorry, this is a definition. I'm defining this new function. Yes. I'm making it in time. No, sorry. Where is the time derivative? I'm doing the Fourier transform from time to frequency. Yes. Time derivatives. Yes. Sorry, this is the second time derivative? No. Yes, sorry. Yeah, this is, yes, second derivative with respect to the 0 component. Sorry, yes. Yes, sorry, yes. So this is the Laplacian that is here, and then you get the second time the omega squared from this term. Yeah, sorry, yes. No, no, good, good. No, no, yes, it was very small. Yes. 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 No, this includes the potential. So yes, but what I'm saying is that that's gonna be. Sorry, no. What you can see actually, if you do the calculation, what you see is that you only have, because the potential is static. Your Riemann, it's only, maybe I even have written here. I think so. Yeah. So the only non-zero components of the Riemann is Riemann J 0K0 and minus Riemann J 0K. And this is second spatial derivatives with respect to the potential, because the potential is static, so you only have derivative with respect to a space. And then actually what you can see is that this, when you couple it to your gravitational waves, because the because the mu, the zero components of the gravitational waves can be fixed to zero. Actually, when you couple, the only terms that you can couple here would be those with some zeros here, and actually those disappear. Yes. I have left, by the way, in the repository some Mathematica notebook where you can compute the Riemann tensors directly with some code in Mathematica. So if people, if you are interested in seeing all the details there, that's maybe a good place. But yeah, that's a good question. So we have this amplification function, and then actually it still comes a bit of work. But essentially, what you do is you want to rewrite this equation in terms of f. So these are spatial derivatives with respect to r of f, and then you have 1 over r squared, and then you have the Laplacian of the angular components, and then you have 2i omega first derivative with respect to f, and then you have 4 times phi omega squared f. So this would be the equation once you put this definition. And then the next thing that you need to do is you need to make the next approximation that we're going to make is we're going to make what is known as the, well, first we're going to assume that because we are in a weak field, then the deflection angle is small, and therefore, whenever we have, this would be the Laplacian in the 2D sphere. Actually, you can simplify this to be a plane. So essentially, anything which have like sines of theta becomes theta. And then the other approximation that one needs to make is you need to say, you need to consider that the second times derivatives with respect to r of f, that those are going to be small compared to the 2 times I omega partial derivative with respect to f. So what this is saying essentially is that the length scale of the variation of the potential is larger than the length scale associated with the wave itself. And if you do that, then you get to something quite interesting. because then your equation, let me do it here, your equation can be written in this form. This is I divided by omega partial r of f equals to -1, 2 omega square, r square, and then delta square theta of f times 2 times phi f. And this is something that you, I don't know, maybe doesn't tell you anything, but actually it resembles very much this equation that I'm sure you all know. So if I write this equation, you will recognize that I'm talking about the Schrödinger equation. So actually, this problem has arrived to a situation which is analogous to that of quantum mechanics, but instead of h bar, actually what we have is 1 over omega, and then here also it's a bit weird, but instead of m, we have 1 over r squared, and then the potential is 2 times phi. So this is interesting because then actually you could write the Lagrangian, and I know that Gonzalo doesn't like Lagrangians, but I know, I'm joking. You can write the Lagrangian, you love them too much, of this problem, and this would be nothing but r squared 2 dot. And then here, to make it more analogous, I'm defining this vector theta dot as the derivative with respect to r, and just that, so that it resembles more the quantum mechanic aspect. And then when we do that, the nice thing is that then we can actually solve, we have methods to solve this problem. And in particular, we can solve this problem using the path integral. So we can use the path integral formulation in which our amplification function f would be of omega at the position of the observer. This would be the differential over all the possible paths of the exponential of I omega of the integral of from 0 to the observer, dr of our Lagrangian. So several points here. One is that this is what this is doing is you are integrating over all paths. The other interesting point is that here you reach the classical limit when your frequency is very large, which this actually corresponds to the limit of geometric optics propagation that we were seeing the first day. Sorry, the other day, when you can do the short wave expansion. And then the other thing is that actually in the context of lensing, actually this quantity, this whole quantity really is telling you about the time delay. So it's telling you about how much your wave is being delayed as it passes through the lens. So this time delay has two components. One is the geometric time delay that accounts for the fact that the path that the gravitational wave could take, or any wave actually could take, is not straight. So the fact that from the source to the observer, you could have something which is not straight. But then you need to account for the fact that there is a mass here, and that's gonna redshift also your signal, and that's the Shapiro delay. So the Shapiro delay accounts from the fact that you have a gravitational potential. So in the context of this analogy with the Lagrangian, the kinetic term gives you the geometric time delay. So this is the Shapiro delay. And this is the geometric time delay. Sorry to put things almost on top of each other, but these are the two pieces that one has at hand. Is it clear where we are going? We haven't finished yet, but we are almost there. Yes, please. Yeah, so the analogy is, I mean, this is just mathematical. Yeah. Yes. Yeah, so I think the interesting, I think the physical way of understanding this is that your waves can actually take different paths, could take different paths from the source to the observer, and they could actually interfere with each other, and that's what is going to lead to your solution. Now, in practice, and this is something that we are going to see in a second, not all the paths are relevant, and typically only a few of the paths are relevant, so that then you are actually in a different regime in which you have not the waves interfering with each other, but independent waves that are propagating separately. Yes, Andres. Yes, yes. Yes. Yeah, so if you don't have a lens, if you don't have the potential, then you just have a straight propagation. Yeah. Yes. 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 So I introduced the Lagrangian to actually try to solve it using the path integral method. That's the approach I took. It's not so that it's only for that purpose. So in the sense that you know from quantum mechanics that this equation of motion comes from a Lagrangian. So I'm saying, okay, this equation of motion would come from this Lagrangian, and then instead of solving the equation of motion this way, there is also the alternative way of solving it, which is with an integral solution, which is the path integral. It's just that you know that already from that connection that there is this tool, which is an integral solution. So if you want, essentially the main point is that instead of solving a differential equation, we are solving it an integral there. That's the connection I did. But it is not, actually you can get the result in through different ways. The same. well, what you have, I mean, I don't know how much I want to get into into this question. It's a good question, but you can define your solutions through a given Lagrangian, and then that accounts for. Yeah, maybe why don't we can we discuss later about that? I think it goes a bit. I think it's a good question, but I just wanted to find a solution to that equation, and instead of just saying, okay, this is a differential equation, I solve it numerically. I tell you, okay, I can write it as an integral, and that's mostly what I'm trying to do here. Sorry to deflect the question. Anyhow, the last approximation that we want to make to get the final result is what is known as the thin lens approximation. And this is just coming from the fact that when you are in cosmological situations, the distance from the source to the lens and from the lens to the observer is actually much larger than the size of the lens itself. So therefore, actually, one can think of the problem of studying this lensing problem as if the lens was only encoded in a plane. So this is what is known as the lens plane. And this is described by some vector theta. And then the whole problem of here then would be to connect different positions in the source plane that we are going to call with vector theta s to trajectories. So we want to see if I have a wave coming from here, what would be the trajectory that appears there. And in essence, also what this is making is that all the effect of lensing is actually kind of happening at a single distance. So I'm kind of assuming that there is a delta function, if you want, of density at this particular distance. And when you do that, what you can get is an expression for f, which is the following. So I have an expression of f that depends on the frequency and the source positions. That's the input that you give. And then there is this term here that I'm going to explain in a second. CRLS. But then here, what you are going to recognize is that, first of all, instead of having this integral over all the possible paths, now I just have an integral over the two components of the lens plane. And then what I have is an exponential of I times omega, and now I have my time delay, which the time delay in this thin lens approximation can be simplified to this. And I'm going to define the variables in a second. So this is the geometric time delay. And then I have the Shapiro time delay. So here I'm defining this distance RL to the lens, and then this distance RS to the source, and then this distance between the lens and the source. And then I need to define as well, so this is the geometric time delay that I was referring there. And this is the Shapiro delay, which is nothing but 2 times the integral of phi over dr. And then this term here is just a normalization so that when phi is 0, so when there is no lensing, what we want is that f is equals to 1. Because then what this means is that our solution of the wave solution is just the initial wave. Okay? And then what one can do actually is one can promote this result to a cosmological setup. And essentially, what happens is that you need to multiply by 1 plus c here, and then these distances, they become angular diameter distances, which I'm gonna define. So the angular diameter distance, this is just the physical distance divided by 1 plus c, or the luminosity distance divided by 1 plus c squared. This is the angular diameter distance. And then the only place you need to change again is you need to add a 1 plus c here. So this is actually the main result. And it's quite interesting because what is telling us is that we are going to have, so our solution to the problem of lensing in a frequency domain, this is going to be this amplification function that depends on omega times the initial signal. So what this means is that because of this frequency dependence, is that when you go to time domain and you compute the lens signal, this waveform that you would get can be distorted. And that's just because of the new dependence in frequency that is going to change your wave, and this can be distorted actually due to the interference and diffraction of the different of the wave traveling near the lens. Now, this is not the actually this is the general case. So I mean, maybe I should well, can doesn't mean that always needs to be distorted, but it's possible that it's distorted. But actually, what is interesting is that this solution actually that can also be written in this more compact way. So if you define some dimensionless frequency and times and angular positions, which I'm going to define in a second. So you can rewrite that expression in this way. So this is just I'm defining a given reference angular scale. So this is a reference angular scale that typically people define as the Einstein radius, but that's not important for us at the moment. But you can, if we define this angular scale, we can normalize our angular positions in the lens plane and in the source plane. And we can also normalize the frequencies so that we have a dimensionless frequency W, which is just 1 plus zeta L, then dl, ds c dls theta square, theta star square, omega. And one can also do the same for the time delays and define a dimensionless time delay. Td, tau d, theta square, where tau d is just this thing here. Anyhow, what is important is that I'm just, well, it's not really important, it's just for convenience, you can redefine this integral in dimensionless quantity, and you get something which is here very compact. This equation, this diffraction integral in general is very complicated to solve. But for example, if you have a point mass potential, and I don't have time to explain this, but has a potential which is given by the logarithm of the absolute value of x. Actually, if you have this potential, this integral can be solved analytically, which is in terms of hypergeometric functions. Well, let me just say it can be solved analytically. But in general, it cannot be solved. Now there is a regime, and with this I will finish, which is interesting, because when the time delay times the frequency is a large number, then this integral can be solved using the stationary phase approximation. And this is something which is done in the notes, and perhaps you could do as an exercise, is that in the limit, so the stationary phase approximation, so when this W times the time delay is a quantity which is large, so when this exponent here is large, this integral is going to be dominated by the stationary points. So the integral is going to be dominated by the points in which the time delay with respect to x is 0. So these are the stationary points. So then what you can do is you can take, so the stationary points I define as xj. So when you have this in this limit, then your time delay, you can expand around these stationary points. So the first term, which will be just the time delay evaluated at the stationary points. Then you will have the first time derivative. This is just a Taylor expansion. And then you will have the second time derivative, xa, xb, and then you have x minus x, xa, j. Well, let me put it here, j. xb minus xb, j, and then you could have higher orders. But of course, as you may have already noticed, this term here, just by the definition of the stationary points, is going to be 0. So then what it means is that we are going to have this term, which is evaluated at the stationary points. So therefore, you can take out of this integral, because this integral is over x, and here there is no dependent on x. So actually, the only term that you have to account in your integral, well, the first term that you need to account in your integral in this stationary phase approximation is this quadratic term. And now you may know, of course, that if you have an integral of the exponential of a quadratic function, this is just a Gaussian integral. So this is something actually that can be solved. And the solution is, in fact, that your amplification function is going to be a sum over all your stationary points. So for every stationary point, you can do this expansion. So you're going to have a sum over them. And then you're going to have one term, which is going to be the square root of the absolute value of mu, which is the magnification at this particular stationary point. And then one has the exponential of the I times W times the time delay of this particular stationary point minus I times NJ pi half. So what this is telling us is actually very interesting because it's telling us that our initial gravitational waves could be split into multiple chirps. Each of these chirps could have a different magnification. It will arrive at a different time delay, and it could have a different phase, Morse phase. And in particular, this the magnification here, mu, is just given by the inverse of the determinant of the Hessian matrix TAV, which this Hessian matrix is just these second derivatives of the time delay surface. So the second derivative of the time delay surface give you the magnification, and then the Morse phase, which can get 3 different values, 0, 1, or 2, actually depends on the type of solution of the lensing potential, and actually depends on the eigenvalues of this matrix. But the important thing, because I need to finish, is that in general, lensing can lead to frequency-dependent modifications of the waveform. But if you are in a regime in which this quantity is large, and this is going to happen whenever the length is the length scale of the, roughly speaking, is when the size of the lens is larger than the wavelength of the gravitational wave. So for example, if you have a galaxy, which is a lens, and you're compared to a gravitational waves, then the effect of lensing is to potentially produce multiple images. It doesn't have to, it can be only a single image, but potentially can produce multiple images. And each of the images will have a different magnification. So the different magnification is important because then what it's going to make is our the inference that we have of the luminosity distance is going to change. And then each of these chirps is going to arrive at a different time, and it can have a different phase. And there are many things which are actually very interesting about lensing. I don't have time to cover over them, so please do ask me later if you have questions. But I should take questions now. Thank you.
Yes.
So I will have just a really basic one about the lensing part. Is it possible that this lensing affects other regions of the spiral of the waveform? Because in here you're showing in spiral phase and chirp, but maybe it affects the part that is driven by the you need numerical relativity or these effects.
So the effect of lensing is going to be determined by this function.
Right.
So typically, you could have the absolute value of f as a function of frequency. Could be something that at low frequencies, actually this is 1, because at low frequencies, essentially, if the wave is much larger than and this is the dimensionless frequency W. So if this is small, this means that the wave is much larger than the lens, and then it doesn't fill the lens. Right. So you are in this regime, and then typically it does something, and then at some point start to oscillate. This region of high oscillation is precisely this part of the stationary phase when you can produce multiple images, and this region here, kind of here, is the interesting part where you can have distortions. Now, your gravitational wave, depending on the relation between its frequency evolution and the mass of the lens, can happen in different parts of here. So it could be that you could, so in general, you're going to affect differently the in-spiral from the merger part. Yeah, it's a good question. Thank you.
Thanks for the lecture. When these distortions occur, is it hard to distinguish them from other effects like orbital precession or eccentricity?
Yes, that's an excellent question. Actually, so if you want to claim that you have observed lensing, you better be sure there is not another known effect, such as you are mentioning, for example, orbital precession. So what you have to do in practice is you need to do the inference of the parameters that define your lens model together with the parameters that define your gravitational wave. And then some of them would be degenerate, but others not. It really depends because, for example, you could have a situation in which you have one chirp, and then you have the other chirp, and actually the total signal, and well, I'm not going to be able to write it to draw it on top, would be kind of like a sum of these two. Now, in this, what this is going to make is that in the part of the in-spiral, yeah, it's hard to draw. In the part of the spiral, though, you could have some modulations of the amplitude. And this is, for example, degenerate with precession. But now if you are looking at if you are able to see the end part, and depending on if you see one merger, and then kind of like on top another merger, that's something which is very different. So it actually depends a bit, again, on the concrete parameters of the system, whether it's easier or more difficult to distinguish. But what you have to do for sure is to analyze both things simultaneously.
But then I guess like you would do one analysis assuming you have a lens system and one without, and like compute the base factors?
Exactly, both? Yes, exactly. So the way we quantify this statistically is by doing the inference with both hypotheses and see which one is favored by the data. Yeah.
I have a couple of questions. So one, is there any kind of expectation for there to be signals that are lensed by objects within the galaxy?
Yes. So actually, the most likely signals that we could get nowadays, so lensing becomes more probable when its source is at higher redshift. So in order to detect these high redshift signals, you need some of the images to be magnified so that they can have an amplitude which is large enough for us to detect. And then if you have high magnifications, actually what this is also doing in some sense is also amplifying all the potential effects of small objects which are around the images that are being formed. In fact, the more you magnify, the more you would expect small scale effects to be relevant. So you could have actually, something which is very interesting is that you could have simultaneously multiple chirps, and some of your chirps could be also lensed by small objects, and you could have also distortions in some of them. Yes.
And I think maybe that leads a little bit into the next one, which is what are the kind of search strategies like in terms of the ranges of redshift and
yes, so
amplification that are
for the distortions, as we were just mentioning, we do it analyzing the data with both hypotheses, and then we compute base factors. Now, for the multiple chirps, it's kind of tricky in the sense that you have a catalog of events, and the question that you are trying to answer is whether some of two or more of these events are actually not independent, but rather they come from the same event. They are from the same source. And for that, what you look is for events which are consistent in their detector frame masses, because lensing does change the luminosity distance, but the detector frame mass is the same spins, the same sky localization, and that's because in general, lensing will change the angular position of the images, but that's so small compared to our angular resolution that you can say that they come from the same region of the sky. And then you look for events that have a phase that is consistent with each other or that differs only by these factors here. Now, this in principle sounds easy, but then in practice, because our detectors don't measure that well the parameters, it's difficult because just by random chance, you would have events with same masses, same sky positions. And then you need to ask, okay, what is the likelihood that I have observed two events from a random population of unlensed events or from a lensed event? And this only becomes worse as you increase the catalog, because the number of pairs that you can form in your catalog grows as n squared. So actually, yeah, there are some challenges there. I will stop because I can speak on this for a long time.
I keep looking at that path integral.
Yes.
And I have a more basic question.
Yes.
Can I understand it as a scattering problem? And in that sense, calculate any point functions?
I don't know. I think, to me, the useful understanding of the path integral is that it allows you to consider all the paths at the same time and how they interact with each other. And that's relevant in the sense that actually, the physical thing that is happening is that a lens can produce multiple images, but those images, if the time delay is close enough, they are going to be interfering with each other. And I think that's the part that I think is nice that you can account into that. For the scattering part, I'm not so sure what would be the interpretation. Maybe someone else have an idea. I don't know.
Thank you.
More questions? I have a very simple question. Is there any difference between gravitational lensing of gravitational waves and gravitational lensing of electromagnetic waves?
Yes. So actually, in the formalism that we have done, no, because what we have been studying is just box of H, and this is equal 0, and this is, well, we were focusing on each of the polarizations, but it will be exactly the same for an electromagnetic wave. Now, what is different from gravitational waves is that we are sensitive to the full waveform, so we coherently observe the wave. While in electromagnetic waves, typically what you get is just the intensity, which would be, if in this case, kind of like, you are just counting how many photons you have. So actually, with electromagnetic waves, you can see magnifications, but then typically you are not sensitive to these frequency-dependent effects. On the other hand, with electromagnetic waves, the angular resolution is much better, and then you can see actually the different positions of the images, because each of these stationary points, they are in different parts of the lens plane, and you can actually see that while with gravitational wave, you cannot see that. So I think both have different aspects. Yeah.
Okay. Yes.
And maybe perhaps another thing, just to advertise gravitational waves as well, is that our time resolution goes down to the milliseconds. So what this means is that you can probe time delays induced by lenses which are very small. So related to the previous question about the substructure, with gravitational waves, you can easily go to smaller scales. Yeah.
In this case, the gravitational waves, if they're also the magnification too?
Yes, so they are magnified as well. Sorry, I mean, they can be both magnify and demagnify. So this can be larger or smaller than one. But then for what we expect, we are biased towards those which are magnified because those would be the ones that we can see farther away.
So maybe just a comment about his question. Maybe he was thinking about this Bohr approximation, where
Yes.
there's only one scattering, and I think that's what you're having, right? You're
Yes.
just assuming.
Actually, well, okay, sorry. Yes, so
Maybe.
the thin lens approximation is kind of like the Bohr scattering, yes. If that was you, yes.
I'm not sure if that was your question, but that's what he's doing.
That's what I'm doing, exactly. Exactly.
Okay. Very good. Many questions. That's fantastic.
Thank you for staying so long. Yes.
So let's thank Jose again and all the speakers. Okay.
Yeah.
So get some rest because there's more tomorrow.
Yes.